Okay, so in section PD, which was properties of dimension, there just weren't that many really good homework problems to use as examples. All of them are assigned. So because of that, we're going to look to some of the example problems from the chapter. This one is on the basis of a polynomial space revisited. And what we want to do is kind of look at this Goldilocks theorem. So let's take a look at it. Basically, in a previous problem, we showed that B was a basis for a polynomial in N. And of course, that's just the set of 1x, x squared, x cubed, all the way up to x to the n. And what I want to show is if this is a basis for the polynomial in N, then so will be C. And you can see that C is 1 plus x, 1 plus x plus x squared, 1 plus x cubed, all the way up to 1 plus x squared plus x cubed, all the way up to x to the n. So it's a set of completely expanded polynomials, whereas B was the individual polynomials. We can see that C is going to be built out of a linear combination of B, but the question is that sufficient to make C also a basis? So let's take a look at why this may be so. First, let's look at why B is a basis for Pn. So there's three conditions that have to be met. Number one, B has to be a subset of Pn. And of course, we can see that that is true because Pn is all the polynomials up to n, and of course, B contains all the polynomials up to n. A linear combination of B, if we spanned it, then it would certainly span this set. So we know right away it's a subset of it because it would span it. Next, 2, we know that B has to be linearly independent. And of course, to do that, we have to look at how we would form this. So is B linearly independent? And to see that, all I need to do is imagine writing this out in an expanded form. So I would have coefficient of A times the first vector. That would give me that 1. So each one of these columns is going to be representative of a certain polynomial order. So there would be 1, 0, 0, all the way down to 0. And there would be n members of this column vector, plus B, and then this would be the x term. So it would be 0, 1, and then zeros all the way down until we got to the nth entry. And you can see I'll add C to the next one. This will be the x squared, so it would be 0, 0, 1, and then zeros all the way down to the last entry. And then we would do this all the way down until we got to our very last entry, whatever alphabetical letter that is. I'll just say A to the N. And then this would actually be the second to last entry, because here we would have zeros all the way down, and then the second to last entry would be 1, and the last one would be a 0, because the very last one's going to be a n plus 1. We'll need a n plus 1 coefficients to fill this out. The very last one would be zeros all the way down and would have a 1 in the last entry. To know that it's a n plus 1 variables that'll actually form the spanning set, we can see that because the first one spans 1, which is a x to the 0, and then it takes the second one to span x to the first, and the third one to span x to the second. So by the time we get to the last one, a to the n plus 1 will be the one necessary for x to the n. So that's why there's n plus 1 entries. So there it is. If I then took all of these vectors and I made a single matrix from it, it's going to look like the identity matrix. And because of that, I know that it will form a linearly independent set. So it'll be 1s all along the diagonal and 0s everywhere else. So this is what this matrix will look like. And that means, is it linearly independent? Yes, it is. because it'll only have the trivial solution if we set this all equal to 0. So that proves then that B is a basis for Pn. B is a basis for Pn because it is a subset of it and it's linearly independent. So let's look at how many members it has. That's what the Goldilocks theorem does, is it tracks whether some set of vectors is a subset of another, and then it basically asks, well, what's the dimension? And of course, the dimension here is going to be n plus 1. That's how many vectors it takes in order to build the span of this set. So B contains n plus 1. The dimension of B is equal to n plus 1. Well, it turns out that's the dimension of C also, which equals the dimension of C. So now all I have to do to prove that C is a spanning set for Pn and consequently forms a basis for it, I don't have to really do this whole matrix thing. All I have to do is look at two things. Is C linearly independent? And you can see I can build another matrix for C that basically does a similar thing. C will have 1, and then the next one will be 1, 1, and the third one's going to be 1, 1, 1, and the fourth and fifth, all the way down. It's going to look very much like this set, except it'll be a triangular matrix. It'll have 1 here, 2 1s, 3 1s, 4 1s. In essence, if I take and find the reduced row echelon form of that, C will turn out to be linearly independent too. So I have two subsets of my full set of polynomials in N. They both have the same dimension, and they are linearly independent of each other. What does that mean? Well, that means by theorem G, the Goldilocks theorem, I can conclude that C spans the polynomials in N, and therefore it is a basis. So this is a really valuable theorem. It's going to allow you to conclude that one vector set spans another, and as a basis of that, if it shares two properties with another basis, and that is that it shares the same dimension and it is also a subset. So if it shares the same dimension and is a subset, then it has to be a spanning set and is therefore a basis.